Okay, the next situation, we have an increment of wire, or a length of wire that goes from -10 to 10 centimeters on the x-axis. That's given, so you would naturally immediately draw yourself an x-axis and label -10 centimeters, 10 centimeters, and probably actually put a little mark there and a little mark there to indicate exactly where that is. The one thing I would recommend to everybody, whether you're in my class or watching this from someplace else, is make your picture big enough to insert stuff into. In class, I see people who've been through multivariable calculus, they're in differential equations, they're taking engineering courses, and they're drawing pictures, little tiny pictures like this to indicate something. Draw a bigger picture, because you're never going to get everything into the picture that you want to, and you don't want to have to redraw it. You've got enough paper, we've got plenty of scrap paper here, you can use it. Okay, so that's one aspect. The other is you want to find the magnetic field due to the current in this wire, which is given to be 50 amps, at the 0.01 meter. I might have said 1 centimeter, but of course, that's neither here nor there. But it's 0.01 meter, it's 1 centimeter. Well, that's a point on the z-axis, so you might as well sketch that point and a z-axis. Now, 1 centimeter would actually be a little smaller than that, but I'd exaggerate the scale here a little bit. Not much, so that I can draw a vector, if necessary, from some point out here to this point, hint, hint, and not have it look like it's right along the x-axis. Okay, so the first thing I ask people to do, and we really are getting to the point where you need to know to do this. It's a skill you should have begun to master in first year calculus. I remember it's probably my third semester of college when I was taking multivariable calculus and electromagnetism. Well, I had taken multivariable calculus when I started to really see what was going on with partitioning intervals and writing integrals. I'd done it, I'd imitated it. It takes a while to sink in. At the stage of this course, having had multivariable calculus and a lot of stuff, you should be mastering this at least by the end of this course. Okay. So, the next thing I ask you to do is, okay, we're going to partition this. Actually, I didn't even mention a partition. I just said, because that should be automatic. You should understand. If we're going to try to find the magnetic field here due to the current in this segment, in this interval, we're going to want the contribution of the current from a typical subinterval. Now that subinterval is going to be a typical increment of our partition, okay, because we always set up an integral by partitioning some interval. In this case, we're going to partition the interval from -10 centimeters to 10 centimeters, and that's implicit when we say, let's take a typical interval of length delta L, and tell me, show me that interval, and tell me where it is. It's an arbitrary interval, so you can't say it's at 5 centimeters or it's at 7 centimeters. Now, if you want to do an interval at 5 centimeters or 7 centimeters and work out the numbers to get yourself familiar with what we're talking about, okay, but it's going to be an arbitrary interval, so you're going to have to replace that 5 centimeters or 7 centimeters or whatever, your position along the x-axis, or -3 centimeters, whatever it is. You're going to have to replace that by some symbol. So, people, the first couple intervals I saw were out about here. Now I kind of enlarged it down here. So we have a delta L interval. Where is it? Okay, well, it's somewhere on the x-axis. It's going to have some x-coordinate, and we should know by now that that x-coordinate is going to be the sample point we use to calculate anything that depends on where this interval is. And we're going to call that sample point, and we've used x star. Okay? So within this picture, that interval is here. Here's our delta L interval. And we know we're going to need, in order to find the magnetic field at this point, due to the current that flows in this interval, we're going to need the vector from this interval to this point. That's going to be our R vector. Well, there we have it. What's our R vector? Well, somebody's able to tell me, it's negative x star, because we're going from here back to here, and we're also going up, and that's all, at first the individual gave me. I said, is there anything else? He said, oh yeah, okay, there's 1 centimeter times k. Clearly, the vector from here to here, if x star is our sample point, so I could put x star in here because that's the answer to where is it. Again, from here to here we go negative x star I plus 1 centimeter times k. And if x star is, if your interval's on this side, well, your negative x star is going to be in a positive direction, right? So this vector will always take you from x star to the point 0.01 meter. Now, having done that, we see that our I delta L, if we assume I is in the positive x direction, is going to be 50 amps times delta L times the I vector. So now we've got our I delta L, and we've got our R vector. That's all we need to plug in to our expression, which is the same as it is in any other case. The I delta L is going to be 50 amps times delta L, just as it was here. But then it's going to be times the I vector. Well, just coincidentally, the way I set up my coordinate system, this is the I vector. For everybody else, it was the J vector or the K vector, or maybe even the negative J vector or the negative K vector. And then we cross that with our R vector, and the difference is here that our R vector has 2 components, but still it's going to be easy to cross I with this vector. I cross I is 0, I cross K is negative J. We can write down the expression for the magnitude of this vector. So we can plug all this in here and get the expression for our delta B. And that expression is in terms of delta L and x star. There are no numbers in it other than the 50 amps and the 1 centimeter here and the magnitude of K. Okay. Then we're going to use that. We're going to sum that up and get an integral. Okay? So, we need to write the expression for delta B. Then for the sum of all our delta B's, which will approach some integral with respect to x. Well, you're going to have to fill in the rest of this and ask yourself what happens as we take the limit of this. It's not going to be like this. What we get out in front of our delta L is not going to be constant. We're not going to be able to factor it out. We are going to have to do an integral because x star changes as we go from negative 10 centimeters to 10 centimeters, right? Okay. Now, I ask people to get that done prior to lab on Friday.